So this is the do now. For those of you at home, it's graded, so you would need to turn this in. If you're stuck at home and you're doing this, you can just type in an email and send it to me, hansfurlow@ciscomments.com. All right. But for now, I'm going to pause your video and go over this with the people here. All right. So today we're talking about studying the Earth's surface, beginning chapter 2. So you're going to keep numbering the same way you've been, but we're just starting a new chapter. You do not need to copy any of this. This is just information. So this is a NASA-produced picture using the Advanced Spaceborne Thermal Emissions and Reflection Radiometer called ASTER for short. All right, that's remote sensing. Remote sensing is anything you're using to tell what something is from far away. Okay, so if you use a satellite to tell whether something is flat or mountainous or hot or cool, that's remote sensing. Okay, measures 14 different wavelengths of electromagnetic spectrum ranging from visible to infrared light. And it gives us information on the land surface temperature, reflectance, how much light is being reflected by the land, and the elevation, the mountainousness. Any image or map of the Earth's surface is just a representation. All maps show the data the map maker intended, the best level of accuracy possible. Each representation is valuable in its own way, but has limitations. That's important. All right, so on this slide, just copy the underlying stuff, which I know is most of it, but I'm trying to keep it a little narrow for you. So those of you at home, you would pause now and get these down. Okay, so constructive, they construct things. Destructive, they wear things down. Something like a volcano can be both. Okay, it's destructive in the sense that it might, like Mount St. Helens when it erupted back in like the 80s, I think it was. The whole side of the volcano blew out. Okay, and so that's a destructive, right? But all the lava flow creates new land, new rock, so it's also constructive. Usually, destructive forces though are things like weathering, erosion, stuff like that. Well, if you were paying attention to me and the notes, how would you know what she's doing? And don't be on your phone.
I'm trying to talk about the Mr. Clock situation with my dad because he keeps texting me about it.
Must be hard to text you when you're not supposed to have your phone. All right. So continents are billions of years old. We've dated rocks. We use uranium radio dating, and they are billions of years old. Okay, the Earth itself is somewhere around 4.5, 4.6 billion years old. All right, ocean basins are younger than 180 million years. So everywhere we've gone and collected rock samples from the ocean floor, they are younger than 180 million years old. Okay? That's telling. We'll find out more about that as we go, but that's telling. Continental margin is continental crust, so that's the part of the continent as it's going down into the ocean. The mid-ocean ridge is a mountain ridge, really it's volcanoes, that kind of zippers through the middle of the oceans. And the ocean trenches are the deepest places in the ocean. Usually, they're places where you have an oceanic crust and a continental crust meeting, and you have one plate going under the other. And that drags down the oceanic crust and creates this trench. It could also be two oceanic crusts coming together. And the only constant thing in the universe is change. So the Earth's surface is always changing. It might be something rapid like a volcano going kablooey. It might be something very slow like wind eroding a mountain. Okay, I just got to show who's boss. All right, you do not need to copy this. So we have this picture here. This is the East African Rift Valley. So if I said that Bill and Susie, that a rift was forming in their relationship, what would that mean? Are they getting closer together or farther apart? Farther apart. So what's happening here is this side of the continent and this side of the continent are moving in opposite directions. So we have a rift forming. So we have volcanoes that have been constructive. So they're releasing magma and forming new land along this rift. But they've left craters. Fractures caused by the rifting in the valley are signs that the valley is breaking apart. Streams are eroding downward. So all these little things that look like cracks, that's where water from the top of the peak is running down. And water likes to find the path of least resistance. So it follows the same path and carves it out over time. And then that E there says a landslide scar is seen on the left side of the small, very steep volcano cone near the center of the image. Landslide deposits have traveled outward from the scar. So I believe that's right here. That's the landslide. So you have constructive and destructive in one place. You have the land being ripped apart, but also you have new land forming. All right. I was gonna. What time is it? Yeah. I thought I had a video in here. Have we watched this one? Okay. I'll try and full screen it.
If I want to turn this globe into a flat map, I'm going to have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator Projection. If you're American, you've probably studied this map in school. It's also the projection that Google Maps uses. The Mercator Projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator Projection. But the original purpose of the Mercator Projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa, by a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
The Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really? So if you want to see a map...
Now I'll throw this out there. I've never heard of that before this video. But I can kind of see it, at least as a subconscious thing. Because you look at the northern hemisphere, and you've got like Europe and Russia and Canada and America, and then down here, you don't have as many countries and stuff, and you don't hear about them quite as often, and so I can kind of see that happening. I don't know. Anyway, and I think it's crazy that Greenland looks this huge, and it's actually 14 times smaller than Africa.
Map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up, but on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkle triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer. If you yourself want to book a projection, you can do so by going to thetruesizer.com, which is a fun tool that allows you to drag around whatever country you want around the map and see how it is distorted depending on where it is. I also want to say a big thanks to my co-stop.
Thank you for your attention.